Okay, so it's our pleasure to have here today Adrià Delhom, that's going to talk about ghosts in metric affine gravity. Please, Adrià.
Okay, so let me start by thanking Luis for giving me the opportunity to speak here. And I will be speaking about a work that I developed with José Beltrán Jiménez during some stays at the University of Salamanca and while I was doing my PhD at the University of Valencia. And I will also go through some concepts that might not be familiar for everyone. I mean, I was not really familiar with them when I started this work, so I had to dig in a little bit. And I think it might be interesting, especially for master and PhD students, to review or to see for the first time what's the meaning of these ghosts and instabilities and so on. And because at least to me, it was not a very precise idea when I started to work on this, but it's an important topic because it can immediately rule out theories and it gives you powerful tools to check physical behavior. So I will be starting by a review on instabilities in field theories, okay? It will take, I guess, around 10-15 minutes. And then I will quickly motivate metric affine theories or geometries if you want, and then I will just review the results that we got with José Beltrán in the 3 and 4 points, 3rd and 4th. Okay, so to start, we have to realize that when we talk about instabilities in general, we are dealing with field theories, which are, theories about nature in which the physical content or the physical variables are solutions to partial differential equations. Okay, so instabilities will have to do in the end with the behavior of solutions of partial differential equations. Okay, so typically you give initial conditions to one of these systems and you let it evolve and you see if the solutions behave properly or if they maybe grow unboundedly or if they oscillate or if they have behavior that we can deal with or not. Okay, so first of all, we should notice that stability or instability refers always to the behavior of perturbations on top of a vacuum. A vacuum is a solution, an exact solution of the system of partial differential equations that defines your field theory. So you have your equations, okay, then you find an exact solutions, and then you compute the behavior of perturbations on top of one of these solutions, okay? And then depending on what the perturbations do, then they will be stable or unstable, and there are different kinds of instabilities that we will see, okay? So before going to understand what kind of instabilities we can have, note that some vacua are measured to be physically stable or at least stable up to a very high degree of confidence. Like for instance, we know that the Minkowski vacuum must be a stable vacuum of our fundamental theory because we have made a lot of experiments assuming that the vacuum is Minkowskian and the predictions are correct, right? And we don't see the vacuum around us decay into other stuff because it's not stable. So there are some, in general, when one is looking for a fundamental theory, then one of the key things that one needs to check is that there are some vacuas that are observed in the universe, like the Sitter or Minkowski or stuff like that, which should be, or at least one wants them to be physically stable, because otherwise any perturbation would just mess with them and destabilize them, okay? So keep in mind that strictly stable or not refers always to a given vacuum. However, you can find the statements of a theory is stable or unstable, and that means that there are some physically relevant backgrounds which we have measured to be stable up to a high degree, which we want that they are stable in our theory. So whenever we find a theory which, for example, has an unstable Minkowskian background, we say that the theory itself is unstable, okay? But strictly, stability always refers to perturbations on top of a given vacuum, okay? So what are these instabilities I'm talking about? So we will deal with an example of a scalar field theory because in general, the analysis of the stability can get much more involved, due to the fact that while in scalar field theories, the scalar field always represents one propagating degree of freedom. If you take, for example, a vector field, you know that it has 4 components, but if it's massless, it only propagates 2 degrees of freedom. If it's massive, it propagates 3, but never the 4 of them. And there are constraints, so the analysis is a bit more involved. One has to take into account the constraints before doing the analysis of the instabilities, okay? But for understanding the type of instabilities that can arise, this is the perfect proxy, let's say. So we start with a standard free scalar theory, okay? So we have the Klein-Gordon Lagrangian, which gives this equation of motion, okay? Note that this second time derivative combined with this Nabla operator gives the box, the usual box, and this is the usual Klein-Gordon equation. We know that there are exact solutions to these equations given by, can you see my mouse? Sorry.
Yeah.
Yes, Adrià, yes.
Okay, thank you. So we know that there are exact solutions to these equations given by plane wave solutions, basically, or sums of them, as we know. And these will be solutions provided that these omega and k things that appear here define the well-known dispersion relation, which is real in this case because omega squared is always positive, okay, because these 2 terms are positive, so omega is always real. And these solutions, as we all know, are oscillatory, so they are bounded. There is always a value of the field, which will be the maximum value, if these omega and k are always real, okay? These solutions always also satisfy that the energy density is positive definite, okay? You can compute the 0,0 component of the stress energy tensor, and you see this is positive, this is also positive, and this is also positive. So it's strictly positive definite, the energy. So we say that when the solutions are bounded, then we have real dispersion relations, so that the energies are basically real and bounded, and they are bounded from below, okay? So the energy, there's a minimum of the energy. We say that this vacuum or these solutions are stable, okay? If you compute perturbations on top of these solutions, you will see that they do not grow unboundedly, okay? However, this is not always the case. We can, for example, have a weird metric, which is not an Minkowskian one here, or we can have a background of the scalar field, okay? For instance, consider a profile of the scalar field where its perturbations are propagating. Okay, let me go for an example. So imagine that we are now considering a scalar field theory with this form. Okay, it's a bit artificial and it might not be the best example, but I came up with this while preparing a course. So you have the usual kinetic term, okay, given by this one. You have the mass term. You have a third order coupling, which is phi coupled to 2 derivatives of phi. Okay, so this coupling will be sourcing non-trivial solutions. Okay, so the field equations for this Lagrangian are given by this thing here, and then in the massless case, so when m squared is 0, there are trivial solutions. Okay, so let's say phi of t equal constant. Okay, you can see that since there are always derivatives of phi in all the terms when the mass is 0, then phi equals constant is a solution, and it's a bounded solution. Okay, because you can find, for instance, phi 0 plus 1. It's always bounding phi 0. Okay, it's always greater than phi 0. However, there are both for the massless and massive case, there are non-trivial solutions which have complicated phi of t profiles. Okay, I am not showing them here because it's not relevant, the particular form, but keep in mind that this is just a function of time. Okay, so these are non-trivial vacua of the theory. Okay, so we now want to know if these vacua are stable or not. What we do is consider nth order perturbations, okay, because we can verify that first order perturbations are stable, but then we need to know about second order perturbations and third order and so on, okay, but sometimes it's enough with considering lowest order perturbations. So consider first order perturbations to this background. That is given by assuming that the profile of the field would be the background plus some small corrections, okay? And to find first order perturbations, we consider the second order Lagrangian in these small perturbations, okay? So you basically take these ansatz, plug it in here and expand and take away terms of order phi cube or more, okay, or higher. So you end up having this kind of Lagrangian. So we see the kinetic term for the perturbations. This is the standard one. And this is a modification of the kinetic term, which has to do with the background, okay? So it depends on time, this term here. Then there is also this mixed term with one derivative, so it should be a damping or enhancement term, depending on the signs of the coefficients. And this is weird interaction between the velocities and the field, and there should be, okay, so there's another term here which I think it's relevant, and then there's the mass term, okay? So this gives this, okay, it's the Lagrangian I was showing, it's, okay. So this gives these field equations. You can see the box here, and then you can see that these complicated terms and a modification to the mass term in here, okay? So depending on the signs of phi 2 dots 0 and lambda phi 0, this term, for instance, can get negative, or these terms can induce enhancement in the modes of the field. So this, if this gets negative, you typically have a negative mass and a negative mass squared, and then that implies that there are perturbations which will grow unboundedly, okay? And the same happens for these terms, okay? So I just wanted to show you an example of how you analyze if a vacuum is stable or not, okay? So you find the field equations and the corresponding Lagrangian for perturbations, and then once you have this, you need to analyze what is the dispersion relation associated to these field equations, okay? In general, it will be complicated. It might be complex, and if it's complex, it will be prone to develop instabilities. You can also compute the energy density associated to these perturbations, and it need not be positive definite, or it need not be there doesn't need to be a minimum value of the energy density, so it can be unbounded from below, and that will be a source of instabilities. So all these things that can happen due to these time variable coefficients induced by the background here, all these things that can happen would render this background unstable, okay? So that would imply that phi of t is an unstable vacuum, okay? So what things can happen? So to understand what the kinds of instabilities that we can have, let us go to a general case where instead of considering a background of the scalar field, we just parameterize the effect of the background in these coefficients here that modify the Klein-Gordon Lagrangian, okay? So we consider a particular case where we don't have velocity-dependent interactions and so on. There should be 2 dots here in front of this, on top of this phi, because this is the kinetic term, okay? So let's say all the effects that we have from the phi 0 here, okay? We encoded them in A, B, and mu. And this case is also taking into account cases where the metric is not a Minkowskian metric because we have a non-trivial gravitational background, or maybe if the field interacts with another field, let's say a photon, for example, and we have a non-trivial background for the photon, we can also include this dependence of the background here in A, B, and mu, okay? There will be more general cases with more coefficients, but for understanding, A, B, and mu would be sufficient, okay? So, in general, a Lagrangian like this would lead to this kind of field equations, okay? So it's phi 2 dots, B over A gradient of phi squared plus mu over A phi, okay? So if B and A equal 1 and mu equals m squared, this is the typical Klein-Gordon equation, okay? And this is the typical Klein-Gordon Lagrangian, okay, as you all can see. So when A, B, and mu vary in a characteristic time scale of the background, which I call capital T, here, okay, then this set of field equations will be satisfied, okay? So here, instead of having a 0, you have terms that vary like derivatives of A, of mu, B, and D, okay? But we will assume that our perturbations vary much quickly than the characteristic timescales of the background. So we are assuming that there's a background which is slowly varying, and we want to understand what small perturbations do on top of this background, okay? So the solutions to these equations, they will be given up to terms that vary with the timescale of the background by the functions which are very similar to the Klein-Gordon, the free Klein-Gordon solutions. Okay, so A and B would have variations of the order of the background, and we have the only modification with the mode functions is this square root of B over A here in front of the K. Okay, so these would be solutions up to order t minus 1. So order, I mean, they will be solutions in an interval of time where the background is varying slowly. Okay, these solutions, you can see that they will be solutions with this up to this approximation if the following dispersion relation, so the following relation between omega and k is satisfied. So we have omega squared equals 1 over a b k squared plus mu. Okay. Note that again, if you have b and a equals to 1, then this is the Klein-Gordon dispersion relation if mu over a equals mass squared. Okay. Okay. So the problem with this dispersion relation is that now, due to the signs of a, b, and mu, this can become negative. And if it becomes negative, then we have a complex frequencies, and you know that that implies decay or unbounded growth in general. And again, the energy density also has this form, and it need not be unbounded from below, depending on the particular functions that are a, b, and mu. Okay. So how do we analyze the stability of these theories? Okay. So we have in general four different possibilities. Okay. So we have if a and b are greater than 0 and mu is also greater than 0 or equal to 0, so massless field, then we have stable perturbations where the modified dispersion relationship is real and the energy is bounded from below, and with propagation speed v over a, okay, in units where c equals 1. There's a problem if mu equals 0, because if it's time varying, it can cross to negative values and then instabilities can develop. Okay, so that is a tricky. It's a stable point, but it can be tricky in generic cases. And there can also it can also happen that b is greater than a, and then we have superluminal propagation, which is not necessarily an instability, but it signals that the theory does not have a Lorentz invariant UV completion. Okay. So this is the stable case. So what about the different types of instabilities? There's the tachyonic instability, which is associated to a negative sign of the mass squared, or if you want, an imaginary mass. Okay, so you will have a and b greater than 0, but mu less than 0. Okay, that means that the frequencies will be complex or imaginary for values of k squared smaller than some critical value, okay, depending on the mass of the field. Okay, and this critical value is saying that there would be an instability that will develop in a characteristic time given by this combination. Okay, so the background will be unstable. The modes with the high momentum do not see the instability, but the modes with low momentum see the instability. So keep in mind that low momentum means that they vary slowly. Okay. Maybe not as slowly as the background, but they are not high energy. So the high energy modes would be fine, but the low energy modes would grow unboundedly, and that means that the approximation that the modes are much smaller than the background, you cannot do that anymore, and then you cannot expand your equations in this. So your expansion leaving out terms of order 5 cube or higher does not make sense anymore, because phi is growing unboundedly. Okay. Then you have the case of a less than 0 and b greater than 0, or vice versa. So the product of a and b is less than 0. Okay, that is called a Laplacian instability. And if that happens, then the modified dispersion relation that I was showing here means that omega becomes imaginary for large values of k. So there's, let's say, low momentum modes. They are fine, but there's somewhere when you go to high momentum where you start developing instability. So large momentum mode grow unboundedly, and that means that they will grow arbitrarily fast, because you can always consider higher and higher momentum modes, and the instability time would be smaller and smaller. So in this case, the background is basically unstable with a characteristic instability time of 0, basically. Okay, so you cannot do this. You cannot trust anything if you have a Laplacian instability. And then you can have a ghost instability, okay, which is A and B less than 0. And that implies, if you go here, then A and B less than 0 is, depending on the sign of mu, might be a tachyonic instability or a stable dispersion relationship. But if you go to the energy density, then you can see that, this will be unbounded, okay, in general, from below. So you can have arbitrarily large energy densities with a negative sign, okay? So you can have arbitrarily low energy. That means that if your field is free, then it doesn't mean anything, because you typically conserve the energy of the system, and then it will evolve, and that's all. But if you couple this ghost degree of freedom to other fields, then this ghost can go to more negative and negative values of the energy, and it can create particles with positive energy. So in the end, what happens is that your vacuum decays in a thermal bath of particles with positive energy, and that is allowed by the ghost taking the negative energies, okay? So that you conserve the energy. And in a fundamental theory, that would imply also an infinitely fast vacuum decay. So it's an infinitely fast instability. You can consider cutoffs so that you hide your ghosts, let's say, over some energy scale, and then you might be able to do something below that scale, but it depends on how you do this, okay? But in general, I just wanted to give you a taste of what kind of instabilities that one can find and how bad they are. So we have the tachyonic instabilities, for which at least in short times you can do some and trust some computation of the theory, but then for Laplacian and ghost instabilities, then you cannot trust the theory at all, okay? And before going to my research with Jose Beltran, let me recall a theorem by Ostrogradsky, okay, which is generally, or at least to me, they didn't they didn't tell me that it existed when I was in undergraduate degree. And this is the following. So what happened with the Ostrogradsky theorem is that Lagrangian with higher order time derivatives, okay, so time derivatives of order higher than 1, so second order time derivatives or higher. If you have Lagrangian like this, then you have ghosts in your spectrum, okay, unless these terms can be integrated by parts and put in terms of 1 time derivative, okay. So that is a powerful theorem, especially if you want your theory to be Lorentz invariant, because in that case you need to have the same order of time and space derivatives. So the theorem is forcing you to have only first order derivatives of both time and space in the Lagrangian, okay. So this is more or less the review I wanted to do of instabilities. So before going to instability symmetric affine gravity, let me just motivate a little bit why we consider these theories. Okay, so in the metric affine framework, space-time is a smooth manifold with a Lorentzian metric and an independent affine connection. Okay, so we have in the metric framework, then a smooth manifold with a Lorentzian metric would be all, and you derive the connection from the metric as the Levi-Civita connection. But in this framework, you have an independent affine connection, so that your fundamental fields are both metric and connection, and you derive dynamics for both of them from the action principle. Okay, so you have in here you have 3 different geometric objects. You have the curvature of the affine connection given by Riemann tensor. You have the non-metricity and the torsion. Okay, these 2 objects vanish in the metric framework, so they kind of give you a measure of how non-Riemannian your theory is, if you want. Okay, and this in the metric framework, it just becomes the usual Riemann tensor for the metric. Okay, so one of the motivations for considering this framework was that, as you might know, Stelle discovered a theory of gravity in the metric framework, which was renormalizable. So it could be a UV complete theory. But it led to propagation of Gauss degrees of freedom due to the fact that the Lagrangian has higher order derivatives. So Ostrogramsky theorem applies, and you have Gauss degrees of freedom. And as you could see, that when you have Gauss degrees of freedom, then your backgrounds are basically unstable with an infinitely fast decay rate. And we see that our universe is stable, at least up to the edge of the universe. So that might not be a good fundamental theory, okay? So people were trying to understand if there could be some modifications which would lead to a ghost-free theory, which is also renormalizable. And one of the things that one could think is that, well, in Stelle theory, when you have terms of quadratics in the Riemann or the Ricci tensor, then you have here the connection is the Levi-Civita connection. You have derivatives of the metric, and then you will have here second order derivatives of the metric in the Lagrangian. Okay. In GR, these terms you can integrate them by parts, so they are boundary terms. But in quadratic gravity, you cannot. So they give rise to ghosts. However, if you consider quadratic gravity a la metric affine, okay, you can see that there are only first order derivatives of the connection, and there need not be higher order derivatives of the metric. So Ostrogramsky theorem might not apply, and they might be ghost-free. So are these theories generally free of ghosts? Okay, that was one of the motivations. So before yielding the results, let me just briefly outline an argument which makes you think that it will not be the case. So you can always decompose an affine connection in terms of the Levi-Civita connection of a metric, then a part which has to do with the non-metricity and a part which has to do with the torsion, both vanishing in the metric framework, okay? Then this means that you can rewrite the Riemann tensor of this connection as an object which has G, derivatives of G, second order derivatives of G, and then non-metricity, covariant derivatives, torsion, and covariant derivatives. So these problematic terms will in general also be here. And these are prone to yield instability. So in principle, this doesn't look very promising for general metric affine theories, okay? However, there are examples of ghost-free classes of metric affine theories. For instance, you have Ricci gravity with projective symmetry, which includes f of r gravity, of course, general relativity, and theories where only the symmetric Ricci tensor enters in the action, okay? There are other subclasses with geometric constraints that derived by Percacci and Segin some years ago, and there are also some extensions of Poincare gauge gravity, which are metric affine theories which are ghost-free, okay? So there are examples of classes of metric affine theories which are ghost-free, okay? And for instance, this Ricci-based gravity class, they have nice properties like singularity resolution at the classical level, and there are some speculative ideas in saying that they could yield or they could be an effective theory which encodes quantum effects due to the following argument, okay? So this is a very speculative argument, but it's a nice thing to have in mind just to, I mean, it's just an interesting analogy, okay? So the analogy comes from condensed matter physics, where people realize that crystals can be described in a continuum limit like smooth manifolds, okay? And that allows to give account of from microscopic properties of these crystals, okay? So when you have perfect crystals, so let's say a lattice like this, which is perfectly aligned and there are no defects, the resulting manifold would be Riemannian. However, when you have defects like this point here or these too close or atoms that are from a different species and stuff like that, or this line that ends here and so on, you can develop torsion and non-metricity, okay? And that is well known from condensed matter theory. So The idea is if the spacetime has some granularity or some microstructure in some way similar to a crystal, then there might be a regime in which the continuum limit is better described by a manifold that has torsional non-metricity than a remaining one, okay? Just a speculative idea. So another motivation for metric affine theories. So there are some motivations to consider them, and apparently there are some classes which are ghost-free. So our idea was to test whether all metric affine theories are ghost-free, or maybe ghosts are generic in the metric affine framework, but not in some subclasses, or we wanted to shed some light into this question, okay? And to that end, we basically considered what we call generalized Ricci-based gravity theories, okay? So in Ricci-based gravity, you consider actions of this kind, where you only consider the symmetric part of the Ricci tensor here. And that is because you want projective symmetry to be a symmetry of Ricci-based gravity theories. And projective transformations change the Ricci tensor. Oh, this is a projective transformation, sorry. So it changes the connection by a vector, and it changes the corresponding Ricci tensor by its field strength. So this is antisymmetric, okay? It's like the FE of the electromagnetic vector, okay? So if you consider only the symmetric part of the Ricci, this is invariant under projective transformations, okay? However, if you consider a generalized Ricci-based gravity and you include the antisymmetric part of the Ricci, this is not anymore invariant under projective transformations. And that means that in principle, there are some degrees of freedom which would be related to this vector, in principle, that could be propagated, okay? So one can see that in this general class of Ricci-based gravity theories, well, these are the field equations, and you can solve the connection algebraically in terms of other objects if you have projective symmetry. If not, there is dynamics for this projective mode. But the key thing is that you can define this object, which is called the Einstein frame metric, okay, defined like this. And it's an object that is relevant because it appears in the equations for the connection inside the covariant derivatives, okay? So if you have projective symmetry, this is symmetric, and this is a symmetric object, and it has the status of a metric. And you end up with having the connection equation of general relativity, okay? So if this is not symmetric, then you have a more complicated equation, okay? So you end up with these algebraic equations for the connection, which in the case of Q being symmetric, you can solve as the Levi-Civita connection, okay, of this metric Q. And if Q is not symmetric, then these are the connection field equations of what is called non-symmetric gravity theory, which is basically Einstein-Hilbert theory with a non-symmetric metric, okay? That is the case without projective symmetry. To see that, we can construct the Einstein-like frame for these theories, which basically you can do by linearizing the action. You linearize the action with respect to the Ricci tensor, okay? So if you want, you introduce an auxiliary field, and when you compute the dynamics for this field and introduce it back into the action, it gives you the original action. So you are basically treating with the same theories, okay? And you can see that with this field definition, you can rewrite the action of generalized Ricci-based theory like this, okay? So this would be some Einstein-Hilbert-like term, and this would be a potential or an interaction between the metric and the matter fields. In the case of having projective symmetry, again, this is symmetric, and this is exactly the Einstein-Hilbert action. When you don't have projective symmetry, then this can develop an antisymmetric part, and then there would be extra dynamics, okay, associated with the projective mode. So it would be similar to non-symmetric gravity theories, okay? These theories were known for propagating instabilities, so we kind of reanalyzed the instabilities in these theories, okay? To do that, we consider, we expand the Q object around the symmetric part and then the antisymmetric part, and we considered this to take into account quadratic field definitions, okay, of the antisymmetric part. It's just a technical detail, okay? But you can think this of a splitting of Q into the symmetric and antisymmetric part. If you plug this back into this action, okay, here, and expand the Ricci tensor, then you can write again Einstein's Hilbert action, which is this, okay, with the symmetric Q, and then you have this is a gauge kinetic term for B mu nu, which is a two-form field and antisymmetric to index tensor, okay? So this would be the exterior differential of these two forms. So this would be the typical kinetic term for a two-form. A mass term, then you can find couplings with of these two forms of the curvature, which in general would be problematic. And you can find this coupling of the two form to the projective mode, okay? And this is the only kinetic term for the projective mode, and it's going to give you a problem because it's non-standard, and you can see that it will develop a negative sign, okay? So we see two sources of instabilities here. First, this problematic non-standard kinetic term, and then the couplings of the two form with the curvature, okay? Let's see if both introduce instabilities. To that end, we can resort to a technique called the decoupling limit, okay, which is, I mean, it's kind of involved and in the beginning, but if you have doubts, you can ask me and I can give you some material where you can understand it, okay? So to that end, you see that there is a mass term here. So this breaks the gauge invariant. So you want to kind of do the massless limit without losing degrees of freedom, okay? So to that end, that you do the Stuckelberg trick and you resort the gauge invariance by doing this, okay? And well, then you do some computation and so on, and you rewrite this B and gamma fields. You do a filter definition and you write them as this linear combination, okay? But you don't change the dynamics here. When you do this expansion, okay, and you plug it back here in the action, in the flat limit, so the curvatures are all zero, okay? So you only take into account this term, and this term. If you do that, then you find that this is the gauge invariant kinetic term for the B field, okay, which is left the same because this transformation is a gauge transformation, so this is invariant. And then you find that the kinetic term of the projective mode can be written like this. So you see that there is a kinetic term for this vector and a kinetic term for this, for this chi, okay? So these should be understood as the kinetic term for these Stuckelberg fields and the projective mode, okay? But they are diagonalized, okay? And you see that one or the other of the kinetic terms has a negative sign, okay? That means if you go back to the beginning, that means that both A and B are negative. So we have a ghost here, okay, in the spectrum of Ricci-based reality theories without projective symmetry, okay? So we see that the projective mode already develops ghost instability in this case, but then let us understand what happens in an arbitrary Q background, because I consider now a flat background so that I eliminated all these terms, okay? So in an arbitrary background, well, it is known in general that the couplings between the two form and the curvature develop instabilities unless they are of the Hort density type, which are particular classes of Lagrangians whose coefficients are specifically designed not to propagate unstable degrees of freedom, okay? But in general, we might have different backgrounds for Q, so this coupling will not in general satisfy the Hort density type coupling, so they will be developing instabilities. This can be seen by considering the problem with from another point of view, okay? So recall the Einstein-Hilbert-like action, the Einstein frame of the theories, okay? And now expand the connection as the Levi-Civita connection of some object which is asymmetric to tensor H plus something, whatever, okay? You can always do this expansion. And then expand this object, the non-symmetric metric Q, in terms of a symmetric part, which would be this H here, and the antisymmetric part, okay? And you plug this here again, and you have the Einstein-Hilbert Lagrangian, and then you have couplings between the connection and itself, couplings between the connection and the B field, and then a kinetic term for the projective mode of the connection, which you can see here, again sourced by the B field, okay? So you can do similar tricks to the ones above, and you can redefine the connection like this so that you differentiate the projective mode from the rest of it. And then you can see what happens in an arbitrary B background. So when you have an non-trivial profile for the two-form field, what happens to the projective mode, okay? So you go here and you can see, you want to see what happens with the projective mode, so you only consider the the couplings, I mean, the terms in which this appears, and it couples to the B field, because you're considering a non-trivial B vacuum, okay? So the relevant part of the action, the relevant part of the action can be written like this, okay? And in a flat background, this would be in general an identity, okay? So it will be B squared here, and it will have this term, okay? If you diagonalize this again by another field of definition, you might find that it becomes something like this, okay? Where either the kinetic term of the projective mode or the mass term of the two-form field has a chain of sign. And that again would imply that you have ghost instabilities if you analyze it with here, okay? And then in the general case where you are not in a flat background, then here instead of having a B, you will have a general, let's say, fourth order tensor which couples it's a supermetric, let's say, which couples the kinetic term of the projective mode, and then a mass tensor for the B field. And you would avoid the ghost if you could have the lambda and M have opposed signatures, so that there's a minus sign in front of the, I mean, if, for example, this is minus and this is plus, let's say, there's a minus here, and you can take this minus out, and this one also out of the action, and then both will have the right sign, because an overall sign does not change anything. But in order for this transformation to diagonalize the above action, you need that M and lambda have opposite signatures, so that the square can be written like this, okay, which has a positive signature, okay? So you cannot achieve this condition in which your action would be ghost-free. So basically, you are led to having ghost instabilities in arbitrary backgrounds, okay? Then again, the solution for the connection, if you go to the field equations in here, or you derive the field equation from here for this piece of the connection which we still don't know, you can see that the solutions would be of this form, okay? So you would have covariant derivatives of B over 1 plus B, whatever, okay? You could see that this coupling to B is not of the Hordensky type in general, and again, it will be developing Ostrogradskian instabilities, okay? So let me just go over this a bit quickly. So we considered whether matter couplings could heal the instabilities, okay? To that end, basically, we introduced matter couplings. We saw their effect on the connection. So they are adding an arbitrary hypermomentum part, and they are sourcing a part of the connection which is given by this covariant derivatives of P, which is this is the part of the connection which is not the Levi-Civita connection of H, okay? So this happens without matter couplings, and this is introduced by all the matter couplings. But in general, these will not cancel the covariant derivatives of B, okay? Because it does not have the correct algebraic structure. So in general, they will not be able to heal the problematic Navier coupling, okay? Even if we heal these couplings, we still have the ghost associated to the projective mode. So we would be in trouble anyway, okay? Furthermore, if you introduce couplings with the matter and the B field, probably what you will do is to enhance the interaction probability of this field with the others, and then reduce the characteristic timescale of the instability if you consider the theory as an effective theory, okay? So, okay, let me see. Okay, so another thing that we consider is whether there are constraints inspired in geometric ideas which could heal the instabilities, okay? So we saw that if we impose a vanishing torsion from the beginning, so we don't let the connection to be as general as possible, but we impose that it is torsion-free, then the resulting theory is ghost-free, and it's an Einstein-Proca system, okay? This was also being seen to be true for generalized vector distortion constraints. So if we say that the connection is the Levi-Civita connection plus this correction, okay, so we force this epsilon, which was generic before, to be of this form, okay, which has two. It is basically a correction which involves one vector and then the other pseudo vector, if you want. If you consider the formation of this type with these coefficients B1, B2, B3, B4 satisfying this constraint, then your theory is also gauge free. Surprisingly, we tried also to impose vanishing non-metricity. So the connection is free to have torsion, but vanishing non-metricity, and this does not yield gauge-free theories. Okay, this constraint is not enough to freeze the gauge degrees of freedom. Okay. We also consider all other relevant cases like hybrid theories, where the Lagrangian is a function of the rigid tensor of the metric and the rigid tensor of the connection, and then we saw that apart from other kind of instabilities related to higher order terms of this object, then the higher order corrections of this object would source the same kind of instabilities that we were deriving. Okay, and there are also some classes of theories that have been seen to be ghost-free, at least at a perturbative level and around an Minkowskian background. Okay, that's a word by Berkachian saying 2 years ago. However, bear in mind that ensuring stability around Minkowski is not enough to ensure the stability of the full theory, in the sense that there can be relevant and stable backgrounds, like for instance the CETE or things like that. Okay, so how does this translate to generic metric affine theories? Because we did everything within the Ricci-based class. Okay, so as I was saying before, if you recall that the Riemann can be written like this, then in general, unless you fine-tune the coefficients of your Lagrangian, you will have Ostrogradskian instabilities propagating. Okay, so you need, if you build metric affine actions with higher order curvature terms, or in general with non-metricity or torsion terms, this is a 3-index tensor, this is a 3-index tensor with 2 antisymmetric index, and this with a 2-symmetric index. But in general, only particular kinds of couplings to the curvature of the metric will be gauge-free, and that is the content of basically Hordensky theories in general. So unless you fine-tune the coefficients for your Lagrangian to be satisfying the Hordensky interactions, you will develop Ostrogradskian instabilities and ghost instabilities. Okay, even if you fine-tune the coefficients, then you might have that if there is no symmetry which protects them under quantum corrections, then this fine-tuning might be spoiled at the quantum level, and you might be in trouble again. So in general, it's not an easy task to build a robustly stable metric affine theory in general. So these were more or less the conclusions of our work. Okay, so generic metric affine theories do propagate gauge degrees of freedom, even though it was thought that they might be free of them for some years. Projective symmetry or other geometrical restrictions, but these geometrical restrictions do not make much sense within the pure metric affine approach. Okay, so projective symmetry is crucial to avoid ghosts in Ricci-based class and in the general class, though in the general class it's not enough to avoid it. Okay, so as I was saying, the restrictions are not enough to guarantee stability in the general case. Building ghost-free metric affine theories requires a high degree of fine-tuning, which one might be spoiled by quantum corrections. Okay, if it's not achieved or achievable by imposing symmetries to the metric affine sector, which are not anomalous. Okay, and okay, that is basically the conclusion of the talk. And thanks for listening. And just please ask any questions if you want.
Okay, so before we proceed, let us ask everybody to turn on their microphones for a round of applause to Adrià